All right. Hey guys. I am recording this one from home over Thanksgiving break. I want to go ahead and get through 5.2 for you, talking about surface circulation. I'm going to go ahead. There's really some complicated ideas in this one, and I really don't want to overthink or overdo it. Just focus on getting the bold information down on your study guide, and knowing that that basic information for the sake of the test. If there are concepts that you don't understand as we go through this, don't sweat it too much. The stuff in bold is what you need to have written down and memorized. Really just written down. You're going to be using the study guide on the test. So stay with me and focus on the bold parts today for surface circulation. We're gonna go ahead and write this. This heading, surface circulation, does not have its own box, so we're gonna go ahead and put this in the Ekman transport box at the top of your 5.2 page, and include this with the Ekman transport information. So wind drives the strongest ocean currents, which occur in the surface layer. So all the major surface currents on the open ocean, they're driven by wind and then kind of also through heat energy from the sun. Those are the two big driving forces behind currents. So for Ekman transport, we learned about Coriolis effect already. So the wind and the Coriolis effect create a sort of spiral effect in our oceans that's referred to as the Ekman spiral. It creates a column within the ocean of this spiraling water. And as you go farther down, the effect of the wind decreases. So the top part is spiraling more, and then the lower layers are spiraling a little less, and then underneath even a little bit less. And so the greatest impact is at the top, and then less as you go farther down. So the upper part of the water that's the most affected by the wind is called the Ekman layer. And so these micro layers move in different directions. Taken as a whole, moves at 90 degrees from the wind. Again, that's not in bold. Don't worry about that too much. Little image here of how Ekman transport works. You have there's the wind blowing across, and then you see the different layers here. This layer is spinning faster and slower and slower. Again, don't overthink it. Really, the big thing that you need to know is that that Ekman transport is caused by the wind. Yeah, it was in that first part. Yeah. So Ekman transport caused by the wind. Your test question. That's it. That's all you need to know for Ekman transport. All right. So for global surface currents, we're gonna move on. So trade winds move toward the equator, and these equatorial currents that these trade winds produce move parallel to the equator. Really, the big thing that we want to get to is our vocabulary word down here, gyres. So because of the Coriolis effect, these wind-driven surface currents combine into huge circular systems called gyres. These are our large ocean currents. And we're going to go ahead and further define those on our next slide. Go ahead and get this part down. Wind-driven surface currents combine into huge circular systems called gyres. So gyres are, kind of further explain, they are a large system of circulating ocean current caused by large wind movements. So these patterns of ocean current, these large circular patterns of ocean current, are following the large circular patterns that we learned about in 5.1 that are happening throughout the atmosphere due to the Coriolis effect. I'll give you a little image of what this looks like. We've got our large circular patterns here. This is the same, roughly the same pattern that the winds were taking because of the Coriolis effect. And now our currents, our ocean currents, are following the same pattern. All right, we're going to keep on going, try to make this lesson as short as we can. Upwelling. Notice the bold part there, go ahead and write that down. Upwelling is the movement of large volumes of bottom water to the surface. It's caused by Ekman transport. It's usually in very intense but small kind of localized patches. It does not occur everywhere, just in small little areas. Coastal upwelling tends to be seasonal, occurring mainly during the time of year when winds are strong and blow in a direction along the coast. I'll give you an image here of what we're talking about. As the wind is blowing along the coast, that water moves out of the way and needs to be displaced by something, and so the water underneath it comes up. So just think of it in terms of that the surface area here, that water is being moved, and so something has to come up and replace it, and it's basically an upward moving current. We have our gyres that are circular moving surface currents. Upwelling is when a current is bringing water upward, and it's a current that is created as the wind moves this water out of the way. This current brings water up. So the Coriolis effect produces equatorial upwelling. So there's some upwelling that happens near the equator. The north equatorial current transports surface water to the north. We really don't need to worry too much about all this, but upwelling also occurs in a ring around Antarctica as a result of wind and current patterns between the continent, blah, blah. Just focus on that bold part there. We'll try to keep this one as simple as we can. An image there of kind of where this equatorial upwelling occurs. Moving on here, so we don't have a section to write anything down here for a 3-layer ocean. I'll buzz through it quickly, but the reason why I left it off of the study guide is because we've already covered it. This is material that's just coming up again. So just based on density, our ocean is in layers. We have a surface layer. This layer is also known as the mixed layer. It tends to be the warmest because of the sun hitting it, and because of that also is the least dense. The more dense things are gonna sink to the bottom. So our intermediate layer is more dense than the surface layer, and then our bottom layer is the most dense of those layers. Yeah, so we've already done some of this before. We're not worried about stability. So here we get to overturn. Overturn is our next section on the study guide. So sometimes water columns become unstable, meaning that the surface water becomes more dense than the water that is below it. This is going to be usually because of maybe cold temperatures. So as the water gets colder, it's getting more dense, and it becomes more dense than the water below it, which is going to cause it to sink down. So the surface water sinks and mixes with deep water. This process is called overturn. It's a sort of kind of reversing of the water. So the colder stuff will sink and the warmer stuff comes up. So overturn follows a regular seasonal pattern. This is an important part for your test. Follows a regular seasonal pattern in temperate and polar regions, usually occurring in the winter when surface waters are cool. So if surface waters get cold enough during the winter, they become more dense and they sink. That process of these colder waters sinking down, they become more dense because of the temperature, and as they sink down, this kind of really kind of a current that's created is referred to as downwelling. And oceanographers use the characteristics combination of temperature and salinity to follow these large masses of water. They can predict based on temperature and based on salinity how the water is going to move up and down, sort of a roller coaster ride that water goes on throughout the planet based on salinity and temperature and therefore density. Excuse me. Yeah, all right, we're gonna keep on going to get to our last part here, the Great Ocean Conveyor. This is the idea of just this idea that water is constantly on the move around the planet, and the water itself is moving around the planet because of currents and tides. These droplets of water, the energy that is moving through the water, a single droplet of water will not stay in the same place over time. It is going to move around the planet in a predictable but pretty wild pattern. And we refer to this as the Great Ocean Conveyor. So let me talk to you about it for just a moment, and then we'll be done. So after water masses leave the surface, so we've got our downwelling, they're sinking down deep to a depth that's determined based on their density. So whatever point that layer of water is no longer more dense, then it's going to settle in. If it's the most dense water in that area, then it will sink all the way to the bottom. If not, then it will kind of stop when it gets to a layer that is more dense than it. So after water masses leave the surface, they sink to a depth determined by their density. And to sink to the bottom, surface waters must be very dense, cold, and probably very salty as well. So cold, salty water is usually the result of the formation of sea ice. You don't have to write any of that down. Main places, again, you're not writing anything down off of this slide either. You do have one more, I believe, where you'll be writing some information. All right, so the main places where surface overturn reaches the bottom are the Atlantic Ocean, south of Greenland, and then just north of Antarctica. Water masses that originate in these locations sink and spread along the seafloor, forming the North Atlantic deep water and the Antarctic bottom layer. Don't worry about having any of that memorized. So, a little image here of the Great Ocean Conveyor. It is water's on the move around the world. And actually, two more slides here. So the last thing for the Great Ocean Conveyor, this global thermohaline circulation called the Great Ocean Conveyor mixes the ocean roughly every 1,000 years. So this water is on the move, up and down because of density, and then around because of currents. And because of the movement of this water is mixing the ocean over time. And mixes the ocean roughly every 1,000 years. So the Great Ocean Conveyor also regulates Earth's climate, brings dissolved oxygen into the deep sea. That downwelling is incredibly important in bringing oxygen that's towards the surface, bringing it down. The upwelling is equally important. It's bringing nutrients that are down on the bottom and allowing them to come up to the surface. So both of those things end up being very important. And our final note here, you can go ahead and include this under Great Ocean Conveyor, even just on the very bottom of the page, but there is a test question related to this. So fluctuations in surface currents have the ability to cause or end ice ages. So if anything changes in the way that this water is moving, then it has the ability to potentially cause an ice age. We're gonna leave it at that for our surface circulation. 2 more lessons in Unit 5 to go. Hopefully I'll be back at school recording those and not doing it here from home. I hope you guys had a great Thanksgiving and a great week so far. I will talk to you later. Peace.